We're in the middle of talking about four historic models of the atom, and we are at this point, have just finished up talking about the Rutherford model of the atom. And so, in the Rutherford model of the atom, what we call the nuclear atom, and again, it is not nuclear because it's getting ready to blow up, but because it has a nucleus. Following the gold foil experiment, we know that the positive charge is focused at the center in the nucleus, and the electrons are positioned somewhere, somehow outside of that nucleus. And this model of the atom now presents two fundamental physical problems for us that our previous models didn't have. One, what are the boundary conditions? Like, where's the edge of the atom? When you're looking at Dalton's atom, they're tiny submicroscopic spheres. The edge of the atom is the radius of the sphere. And even with Thomson's plum pudding model, we're mostly still considering the atom to be tiny spheres. It's just that contained in those delocalized positively charged spheres are a bunch of electrons stuck in that positive goo like raisins in plum pudding. But following the gold foil experiment and with this Rutherford model you see in front of you, the boundary conditions are not obvious. What is going to make the edge of the atom if the positive charge is focused in one place and the electrons or negative charge is going around that? Second, based on this model as it's presented here, the universe ought all completely implode on itself. Every atom should just collapse into the size of the nucleus, and yet, by all estimations, the universe has yet to completely collapse in on itself. And so, what is maintaining that empty space in the atom, and where is the edge? Well, one of the important figures who began to kind of take a stab at that was a guy by the name of Niels Bohr. Niels Bohr, considering this model of the atom presented by Rutherford, said, where else in nature do we see a central object that is attracting all of the objects that are around the outside, and yet those objects moving around on the outside don't collapse into the center? And he proposed that perhaps it is the case that the electrons are moving in orbital paths. Those orbital paths around the nucleus keep the atom from collapsing into the center. And this has merit. There are certainly analogies we can draw to other systems that do this. And so you get this kind of particular picture of the model that you see in front of you, that even as we're going to look at a couple of more accurate models, this has kind of become the standard bearer of things that are of atomic nature in our society. And so, I mean, you can look at things like logos for companies. Here's someone that apparently got bored and needle stitched an atom. Here's some nice jewelry design. You can even find yourself a good meme. Never trust an atom. They make up everything. But what we're talking about here, of course, is Bohr is looking at the solar system. And he is saying, hey, here we have a central object that has a strong pull towards all the objects outside of it. In this case, it's the sun rather than the nucleus to an atom. And the objects moving around, though they are attracted to the center of this system, because they're moving in orbital paths, they don't fall into the center. Again, best we can tell, the Earth has not collapsed into the sun, so this seems pretty accurate. And so we have this model of the atom with a nucleus at the center, and we have the objects moving around in orbital paths, and because they're moving around in orbital paths, they don't collapse in. This was proposed by Bohr as the planetary model in 1913. And there are two, well, before that, this is our third historic model of the atom, the planetary model. So you can draw that in one of your quadrants of your paper that has the atomic models on it. And there are a couple, again, issues with this. One is just an issue of scale. So you have a solar system versus a nucleus and electrons inside an atom. And the issue of scale means that the analogies don't hold exactly. Also, you have an issue of force. So electromagnetic force is the primary, or electrostatic force, we should say, is the primary force in an atom, whereas gravitational force is the primary force in a solar system. And so there are not perfect analogies to these things. And one of the real significant differences that was recognized by Bohr was the nature of these orbits. In the solar system, the possibility for orbital distances from the sun, gravitational systems, energy is continuous. The planets in our solar system are a particular, on average, distance from the sun, but there's nothing saying they have to be there. And they could certainly have other orbits, and the physics of that would work out just fine. There are other planetary systems orbiting suns in the universe, and their planets are not in the exact same places as our planets. Essentially, any distance from the sun is an allowable orbit. And of course, we send out satellites around the sun to get to certain places in our solar system to take measurements. And again, all of those orbital paths are open to that mathematical analysis. In the planetary model, what Bohr notices that electrons, and there is a fair bit of experimental evidence that suggests this that we'll look at in our next chapter, but the orbits of electrons are quantized. They're fixed. Only certain distances from the nucleus are allowed, and those distances determine the energy of the electron. This is a thing you're not going to see on the slide, but you should definitely write down on your papers. The energy of an electron increases as it moves further away from the nucleus. So the further out that orbit is, the higher energy the electron. The closer that orbit is, the closer the electron. Higher energy means further away from the nucleus. So it's not obvious why this would be. Why are there only fixed positions that electrons could be around the nucleus? And that is kind of the root or the root problem that quantum mechanics is trying to solve. Why do electrons behave the way electrons do? And ultimately, why do really small particles behave the way really small particles do? Let's look at another way to think about this quantized energy situation. The solar system, large objects, classical physics, so think of Isaac Newton and the apple falling to the earth, operate on what's called continuous energy systems. That means the energy of an object can be any value. And so if you think about a situation like a ramp, and where we measure the energy of this object as its height up on the ramp, how high off the ground is it? Again, also then measured by, if we let this object roll, the higher up it starts, the faster it's going to be moving at the bottom. And if you think about these two positions, position 1 at the bottom, position 2 at the top, how many possible positions are there in between those two things? And hopefully in your brain you recognize that the number of points in between any 2 points on any line in geometry is infinite. You can always cut the line in half and 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 in half infinitely. And so the possible energy positions are on a ramp are continuous. They're infinite. Quantized energy is more like a staircase. And so if we're measuring energy as height off the ground and potential to fall to the ground, the starting positions for this object are at each position on the stair. And it does not have continuous energy from E1 to E3. There is only one possible energy in between E1 and E3, and that's E2. Balls tend to not hover in between stair heights as an initial starting position for energy. So quantum mechanics, electrons behave more like a staircase. Classical physics, planets behave more like a ramp. And again, it's not obvious why electrons would do this. The two people to sort out a model for how electrons actually do behave, because not only are their energies fixed, it turns out because these analogies don't perfectly overlap, there are no orbits that can actually be traced for electrons. Electrons have energies due to their average distance from the nucleus, but they can move all about within the atom, or even completely disperse themselves into an energy field rather than a particular particle. If all of that sounds weird, it should, because quantum mechanics is quite weird. The two people to initially kind of sort this out, a guy by the name of Erwin Schrödinger, who is responsible for a thing called wave mechanics. And in wave mechanics, He built models of standing waves where only certain frequencies allow waves to move through any particular medium. And so he built models to represent the quantized energy levels of electrons, whereas Werner Heisenberg primarily built mathematical equations to explain them. And ultimately, a group of scientists picked up on these two approaches to explaining electrons and other small particles, and from that we get quantum mechanics. The model that we build for quantum mechanics is called the electron cloud model, or the quantum mechanical model, where no longer do we consider the electrons to be moving in perfect circular orbits, but the electrons move or operate within an electron cloud, or what we call an orbital. So rather than orbit, we now refer to it as orbital. An orbital is simply a location around the nucleus that describes a probability field. And any particular electron, its orbital is where it's likely to be found in 90% of the time. So again, remember, higher energy for an electron means further away from the nucleus. Well, if you're a higher energy electron, your orbital is going to be a larger cloud, and on average, that electron will be further away from the nucleus. The electron cloud is not a boundary. The electron cloud is, again, a region of space, and as you look in this diagram, the arrows are meant to trace possible trajectories for an electron. Of course, they're not going to move in a straight line for as long as is depicted here. This is just a model, but that electron is perfectly capable of being outside of that cloud. That electron could be all the way over where it says number 4. That electron could be by the L in model at any particular point. That electron could be in Cincinnati, Ohio 10 minutes from now, statistically, right? There's a probability that that electron can be found anywhere in the universe. It's just as you get further and further away from the defined electron cloud, that probability reduces. And the probability of that electron being in Cincinnati, Ohio is, for all intensive purposes, 0. But mathematically, it's not actually 0. So that's our quantum mechanical model. We'll have an entire chapter that will tackle that. For right now, you just need to know an electron cloud or an orbital is a region of space where an electron is likely to be found, rather than expecting the electrons moving in perfect orbits, always equidistant from the nucleus.